Here's an optional lesson on using a different data set. Because you might, after all, be asking, what other data sets can I use? And how do my classifiers perform on these different data sets? So we're going to try and answer those questions by training your algorithms on a different data set and then comparing your algorithms across different data sets. So the data set we've used so far is for Higgs decay to 4 leptons. Let's try a different one to show you the process of using the same algorithms on a different data set. And another thing you'll hopefully realize is that though they might do well, separate optimization is needed for different data sets. So let's discuss this new data set. It's once again real Atlas data, but this time each event corresponds to 2 detected leptons and at least 6 detected jets, at least 2 of which are B-tagged jets. The signal is a rare top quark process called TTZ, and others are background. The analysis we're going to do here closely follows this Atlas published paper studying this rare process. So the signal is called TTZ, and the background processes are called TT bar, Z2HF, Z1HF, Z0HF, and other. Your first challenge, this optional video is going to be full of challenges because you will have practiced on the other data set. First challenge is to define a list called samples TTZ containing other Z1HF, Z2HF, TT bar, and TTZ. Don't worry about Z0HF now. You can add that in later if you want. If you need a clue, you can look at how samples was defined in the data discussion lesson. So pause the video, try and work that out yourself, and then you can resume. Let's go for it. Samples TTZ equals a list, square brackets. We go with other Z1HF, Z2HF, T bar, and TTZ. Okay. Now we'd better explore the dataset a bit. First part of your next challenge is to define an empty dictionary DataFrames TTZ to hold these data frames. If you need a clue, look at the data discussion lesson. And then second part is to loop over these samples and read the CSV files in Kaggle input TTZ CSV into these data frames. So pause and try and work it out. There we go, let's type it together if you haven't done so already. DataFrames TTZ equals an empty dictionary. And then we loop, make a loop for S in samples TTZ. What to do is use the pandas read CSV function to read files in Kaggle /input /TTZ CSV. Dash at the end, plus the name of that sample plus .csv. And we want to read each of these files into the data frames. And the key for that dictionary will be the sample. That should do it. Now, you might be glad to know we've already cleaned up this data set for you and calculated some interesting features so that you can dive straight into the machine learning. In the Atlas paper for this process, there are 17 variables used in their machine learning algorithms. So you definitely don't want to optimize those separately. So we had better use machine learning. So let's start formatting the data for machine learning. Next challenge here is to create a list called ML inputs TTZ of these variables in the data set. So pause and try and work it out. Here we go, if you haven't done it yet. ML inputs equals a list of PT4 jet, PT6 jet, DRLL, and jet. And MBJJ top. BJJ. Should be lowercase. And MBJJ top. HT6. You can add the other variables in later if you want, but let's just start with these. You can find definitions of these variables in the Atlas published paper. Okay, next challenge is to, first of all, create an empty list called allMCTTZ. Then the solution for part 1 is there. So try and work that out before moving on to part 2. And then part 2, create another empty list, allYTTZ. Again, try and work that out before moving on. And then the part 3 is to loop over the samples. 4, if you're currently processing a sample called data, continue. 5, at each pass through the loop, append the subset of the data frame for this sample, contain the columns for ML inputs TTZ to that list, all MC TTZ. If you're currently processing a sample called TTZ, append an array of 1s to all Y TTZ. Otherwise, else append an array of 0s to all Y TTZ. So the solutions for these parts are all together because it's all part of the same for loop. So pause that and try and work it out. We can try and type it together. All MC TTZ equals empty list. It's part 1. Part 2, all Y TTZ equals an empty list. Then we need to do a loop for S in Z. If currently processing a sample called data, so if S is equal to data, we forget about that one and start the next sample through the for loop. We want the same indentation. Append the subset and subset of the data frame. So it's called DataFrames TTZ for this sample. That uses the key S, containing the columns ML inputs TTZ to the list all MC TTZ. So start. Okay, that was part 5. Part 6. If currently processing a sample called TTZ, So if S equals TTZ, append an array of ones, so np.ones, which needs to be the length of TTZ data frame. I believe the syntax for that is, or we could just do len, I believe. Length of. We need to append that to all y TTZ. Same indentation, else all y TTZ dot append an array of zeros of length of frame processing. So let's see if that works. Seems to have worked. Next part of the challenge is concatenate the list all MC TTZ into an array called X TTZ. So pause and try and work that out before moving on to part 2. And then part 2, similarly concatenate the list all y TTZ into an array called y TTZ. Okay, so try and work that one out yourself by pausing. Otherwise we can do it here. So X TTZ equals numpy dot concatenate MC TTZ. That works, yeah. Same for y, np.concatenate y. It seems to be fine. Okay, now let's move on to the next challenge. Define a new random forest classifier called RF classifier TTZ with the same hyperparameters as before as part 1, so try and work that one out. And then part 2, fit your classifier to X TTZ and Y TTZ. So pause and try and work those ones out. And we're back once you've paused it. So we want to call our classifier RFCLF TTZ, and it's a random forest classifier with these hyperparameters, max depth equal 8, and n estimator equals 30. Okay, and then we want to fit FCLF to X TTZ and Y TTZ. Okay, there we go. It's loading, thinking about it. Now we can try apply our new classifier to experimental data. So read data.csv is the first part of the challenge. Then number 2, convert this to a NumPy array called xDataTTZ. Number 3, define an empty list called thresholds TTZ. and 4 define empty lists, weights TTZ and colors TTZ. Okay, so pause and try and work that one out and come back to the video once you've given it a go. Okay, let's remind ourselves how it was done before. It was pd.read CSV. And let's call that one DataFrames TTZ with a key data underscore rather than a dash. So there's part 1. Okay, part 2, convert it to a NumPy array called xData TZ. So we only want the columns corresponding to ML inputs. And we can use the dot values to get the actual numbers. Part 3, define an empty list thresholds TTZ. Oh, yeah. Part 4, empty lists weights TTZ equals TZ equals. Okay. Now we're going to make a plot where we directly compare real experimental data with all simulated data. So let's start this off. We want to loop through the samples. For each sample, we want to append. No, let's step back a bit. For each sample, we want to get the columns corresponding to the ML inputs. Okay. Now that we have that, we want to predict the probabilities using our classifier, using the function predict proba. And we want to get the prediction that it's signal from that, which is just the second column. So of course, 1 starting from 0 index. And then let's append to this list threshold TTZ. Predicted prob signal. Okay. Now then, let's plot each of those thresholds. TTZ is what we're going to histogram. Bins we're going to use between 0 and 1, because that's the output of the random forest. So start at 0, go up to 1.1, remembering that it doesn't use 1.1, it uses the one before that. So 1 and a width of 0.1. Stack them, equals true. Okay, let's see how that looks. See what's going on there. Oh, I didn't say bins equals np dot range. creates the range of bins. And there we go, there's the plot so far. But what was the point of doing these weights? What was the point of defining this empty list weights? Well, simulated events need to be weighted so that the object identification and many other things match those determined from data control samples. So let's think about these weights now. And the weights is simply a column in the DataFrames. We can append that for each sample. DataFrames, TTZ, for this sample. And the column is called total weight, so you can access it that way. And then we just add another argument to our histogram plotting. Weights equals weights, TTZ. Now the contributions are weighted. Okay. Next step, let's think about adding the real experimental data. So we need to do a similar thing to what we did here for the data. We already have a variable called xdata ttz, so we can jump straight into the second step and call it predicted prob data equals rf clf predict proba x z, and again get the signal of it. Second column. And let's histogram the data. With this thing that we just calculated, predicted prob data signal. Using the same bins as before, bins equals np.a range 0, 0.1. Then we want to get the error bars on the data. So data error z. We're just going to use the statistical error, which is the square root of each data point. And then we can plot those error bars using error bar. X is the center of each bin. So this time it's an np.a range between starting at 0.05, ending at 1.05. That means that the last one is 0.95 with a width of 0.1. Y equals data list ttz that we defined 2 lines earlier. And the Y error is the data error ttz. Right, let's run that, see how it looks. What's happened here? I made a typo earlier when I was reading in data CSV. I didn't want S. I know it's called data, so I'll just read in data straight away. Oh, that's much better. Now let's get the data error bars looking actually more like error bars. So we can use the keyword format equals KO for black circular points. There we go. And we definitely want to put a legend, so let's do that. We've got no legend entries yet, so let's fill those. So what we're going to do is, whilst we're plotting, label the names inside samples TTZ. There we go, we've got the labels for the simulated samples, and we should also add a label for the data. Let's call it. And we should also add a x-axis label. Threshold is a good one. Okay, another thing we want to do is add error bars on the simulated samples. And how that's done is to square the weights for each sample, stack them on top of each other, and then take the square root at the end. Okay, so we first need to define a variable that will hold that squared value to it as we go through, and it of course is going to start off at 0, so it's a array of zeros, 10 zeros, 1 for each bin. And then we're going to histogram signal the same bins as before. We've been histogramming for 0, 1.1, and a width of 0.1. And we want to square the weights this time. So it's similar to 4, but it's this one squared. So asterisk asterisk 2. And let's call that weights squared. Add a underscore because we want the first part of what that np.histogram function returns. Then we need to add that to the cumulative MC stat error squared. So we can use this np.add function. What you're adding to start with, and then what you're adding. And then, once we've finished the for loop, we can get the statistical error by taking the square root of all of that. Okay, now we'd better plot that. First of all, we need to get the height of the total stack of simulated samples so that we can start our error bar at the appropriate place. So let's call the plot of histograms MC heights. See how that looks. So it's an array that gets added to each time. Well, it's got two parts to the array. The first part is the y values, and then the second part is the x values. So we only we want the y values, which is the first part. So let's take the 0 element of MC heights. Okay, that is separate lists for each loop through the stacked processes. So we want the last one because that's what it is when it's added the last stacked process. So -1 will get us the MC heights for the total. There we go. And you can check this, for example, for the last bin, it says it's about 22. And yeah, if we go across, it is about 22. Okay, so let's have a variable that we call MC total. Okay. Now we can go to plot the statistical uncertainty. There's going to be a bar chart. The X value is going to be the same as the error bar on the data we made. So np.a range starting at 0.05, going up to 1.05, 0.1. That's the X value. The Y value is going to be 2 times the stat error, one for down and another one for up. Bottom of this bar chart is going to be the total stack minus the MC stat error, so that it starts, goes up to 0, and then the same amount again. So let's plot that to start with. The width of those are way too big, those error bars. So right width equals 0.1. It's those blue things, it seems, so, but they're kind of in the way of the other things. So let's write color equals none. Now we can't see them at all, so we need something to be able to see them. Let's give them a hatch. And there we go, now we can see them and they're not blocking everything. Let's give this a label of uncertainty so that we can also see that in the legend. Yeah, there it is there. Okay, what else? Well, now we're going to choose what colors each of the processes has. Let's define a dictionary of colors. These colors are in hexadecimal, and you'll see why that is the case in a minute. And we've also defined this list of colors TTZ. So let's append to that each time we have a different sample. The way we can do that is by just accessing the colors dict and using the key for that sample. And then to apply that, we would write color equals Z so that the histogram knows to use those colors. And that's it. Now, this is already pretty good because within errors, the real experimental data agree with the simulated data histograms. This is great news. It means our random forest classifier makes sense with real experimental data. And it's already starting to look somewhat similar to figure 10C from the Atlas published paper studying this processes. So basically, you're already recreating science research in your learning. Now, the question for you is, can you do any better? Can you make your graph look more like this published graph? Have we forgotten any steps before applying our machine learning model to data? Another question is, how would a different machine learning model do? So here are some suggestions that you could try to go further. You could add variables into your machine learning models. You could add in the other background samples. You could modify some hyperparameters. You could try a neural network. You could try a BDT, boosted decision tree, and try and give some quantification how important each variable is. With each change, keep an eye on this final experimental data graph. But that's it for this lesson on using a different data set for machine learning. The key points have been that the same algorithm can do fairly well across different data sets. However, different optimization is needed for different data sets to really get the best out of machine learning. And that's it for this video on an optional extension to the machine learning tutorial on a different data set. Enjoy playing around.